Okay, so welcome to the Advanced Gas Dynamics class. So as far as the name is concerned, it seems like we are concerned only about gases. Now this course could have been easily been called as compressible flows. So some of the questions I always request students to ask and also instructors to answer is that, why are we doing this course? Besides obviously the obvious answers to this. So should we be concerned about gas dynamics? Is that important? Do we see that around examples of this around us all the time? Is this a new topic, or people have enough knowledge about this from the previous researchers, etc.? And do we know a lot about it? Are we still learning about it, and so on and so forth, right? So like I said, this course could have been easily called as compressible flows, theories of compressible flows. So does that mean that compressible flows or compressible properties are only a phenomena of gases, or others, fluids for that matter, can be compressible as well? Well, we'll try to answer some of these questions. Like we said, the purpose of this course, the importance of this course, a little bit about history, and what exactly we should be interested in, and of course if we can find novel ways of implementing the knowledge that we acquire as we go along in this course. So what we'll do by starting is a little bit of history and try to understand how this study became, the study of compressible nature of fluids became important, and what exactly triggered studies, or that today we are in a place where we are actually doing a whole course on gas dynamics. Okay, now this is an example which you are probably familiar with. So this is a wheel, as you can see, this is a wheel, and these small little things out here are blades, or buckets if you will, and essentially the wheel is going to rotate, but as you can see there is no mechanical mechanism to move this wheel. Instead we have these four things here, right? Well, these things are called as nozzles. Okay, let's call them just ducts. Okay, and let's sort of try and look at what is so special about that. So essentially what we see is that there is so we have a large slightly wide entrance and a slightly narrow. So we have a large entrance and a narrow exit, right? So let's complete the story first. Okay, so what you see on the wheel is that we have nozzles like this, 4 of its kind, right? And the blue here is essentially steam being injected into these nozzles, right? Steam is injected into these nozzles, it enters through this wider entrance and comes out through this narrow exit, and it comes out and hits these buckets or blades with such an impact that it is able to rotate this wheel at 30,000 RPM, right? And this ingenious way of doing this was first time accomplished by the Swedish engineer called Carl de Laval, and this is also called the Laval's wheel in 1893. So this was the first time he was actually used something like this. So essentially what is it that this is causing it? So we have a stream, a steam coming in, a jet of steam coming in and producing a lot of impact, right? So essentially what is happening is steam comes in and it is choked, that is the technical term to use. So essentially it comes here, it accelerates. There is a corresponding pressure drop. And when it hits the buckets, it's able to rotate it with as high speeds of 30,000 RPM, and that was pretty large at that point of time. right. So this is essentially a convergent nozzle. Okay. Now we can have another type of nozzle as well, like that, where the entrance is narrow and the exit is large, right. So now this is the entrance and this is the exit, and this is a divergent nozzle. Okay. This is a divergent nozzle. Okay. Now what we can do is combine these two. So what we can do is essentially combine these two, right. So what you know as probably something like this. So this is nothing but a convergent divergent nozzle, right. This is the modern day convergent divergent nozzle. So it works on the same principle of the compressible flow, which was used by Laval the first time round. Okay, so this was the first of its kind way back in 1893. Now I'll go over one of these examples, jump over to 1947. Right. You're probably familiar with this picture out here. So this is the Bell XX1, right. So, and this was the pilot, Chuck Yeager, and this was the first time in 1947 that this plane and Yeager was able to break the sound barrier, which means that he was able to fly at a speed which is higher than the speed of sound, which is Mach 1. So basically he was able to break the sound barrier. And why is this important? Why am I bringing this up in terms of Laval's experiment? Well, the reason being that the thrust in the Bell XX1, the thrust in this plane was provided by 4 convergent divergent nozzles, and that was the one which was able to create speeds or move this Bell XX1 at speeds for which he was able to reach Mach. So essentially from a very simple experiment which Laval used, it was basically a Swedish engineer, to a rotator wheel. He used essentially the principles of compressible flow, and we've been able to catapult that and use it for something as sophisticated as supersonic flow. Okay. Now there are, so similarly, we have been able to see application of compressible flow theories in in literature so far. So some of those applications could be internal flow through rockets and gas turbines, high speed flow through wind tunnels, external flow over airplanes for Mach 0.3, re-entry vehicles, etc., flow inside, and IC engines. So what I mean by this is that all people, so from mechanical background or aerospace background, or so and so on and so forth, are all are interested in flows like this, because compressible flow theories are applicable to a wide range of disciplines. Okay. Now I said something about external flow over airplanes for Mach 0.3. It seems like a thumb rule that if the flow over airplanes is less than 0.03, then the compressible nature of the fluid may be overlooked. So we'll try to see what that means. Okay. So we'll try to see that with say an example. For example, let us take an airplane. okay, and say at this point, say A, right, which is far off from the airplane, and we have the speed here. The speed here is 100 miles per hour, which is around 45 meter per second, right. So we have, so let me call this as the free stream. The free stream upstream of this plane is 100 miles per hour. Now this comes over here and it accelerates over the plane, right. It accelerates, and at some point here, say the speed out here is 150 miles per hour, right, which is around 67 meters per second, right. Now as we saw in the example which I showed you just earlier over here, that the flow accelerated, right, there was a corresponding pressure drop, right. So here too what we would like to know is that if the flow is moving, say from, is being accelerated from 100 miles per hour to 150 miles per hour, then what is the corresponding pressure drop, right, and what we should, I mean how we are going to go about finding this, okay. Now first things first, let's do this. Let's just say that this flow out here is incompressible. It's not compressible in nature, okay. So if that happens, and am I sure of that? No, I'm not. So I'm going to just assume it is incompressible and then go and verify that whether my assumption is correct or not. So we'll just say it is incompressible for the time being, and we'll use the Bernoulli's principle between A and B, right. So this is the Bernoulli's principle. So we'll apply that between A and B. So what we will get, so I get a relative pressure drop of pressure change of 1.5%, okay. And now we want to see whether, you know, I used an incompressible theory over here, if I was correct in doing that. If not, then what we will do, okay. So let's move a little forward. Now I keep saying that it is compressible in nature. Now how do we quantify that? How do we put math into this? Okay, I understand that there is a flow over here, there is a corresponding pressure drop. The question is how much? How do I relate the this pressure drop to the speed, or do I have to do that? Can I do that? So I need some sort of quantification, right, to say how much a gas or a fluid is compressible, right, and only based on that can we say that this is an incompressible fluid or this is a compressible fluid. Let's try and find out some sort of quantification for this. Let's do this. So let us say we have a fluid element like this, okay, and this is the pressure and this is the volume, okay. So we have okay. Now say there is an increase in the pressure. I increase the pressure, so there is an increase which is dP, and there is a corresponding change in the volume, right. So I will write this as so this is a corresponding change in volume. Now, if there is an increase in pressure, the volume will decrease, and that we know from our known principles of gases, etc. So, I will note that when I write change here, I actually mean there is a decrease. So, I will denote that by a negative sign. So, if I have a positive pressure change, there is a negative volume change, right. So, negative change basically indicates there is a decrease in the volume. Now, we shall define what I understand by compressibility, right. So, let me write this here. So, compressibility is defined so. Let me call that as tau. So, then I shall write that as every time I write an equation, I always like to say that in words so that I understand what it means, so that I do not have to remember the expression itself. If I know what that means, I can always develop the expression. So, what this means is that fractional change in volume, which is dV by V per unit change in the pressure. So, that is what compressibility means. There is a fractional change in the volume per unit change in pressure, and I can write this as okay, let me call this as, I like to name my equations for further reference. So, that is how I define compressibility. Okay. Now, the next thing we can see here, that if there is a change in the pressure and there is a corresponding change in volume, what happens to the temperature? Now, if there is a change in pressure, there is change in volume, there should be a corresponding change in temperature as well, right. Now, if that is so, what is happening to that over here? Are we taking care of the temperature or no? Now, let us therefore define this compressibility for a few cases where we do that. We say something about the temperature, right. How do we do that? Now, first thing we will see is that we will say is that the temperature is constant, right. And how do we keep the temperature constant? That there is a positive heat transfer, that there is a non-zero heat transfer, right, and as a result of which the temperature is constant. Okay. So, then I can define, then I will write my compressibility in this form. Okay. And we can call this, I think you should have guessed by now, that this is isothermal compressibility. So, this is isothermal compressibility. Okay. So, in this case the temperature is constant. Okay. Now, some things to notice here is that when I write these subscripts out here, right. So, I write T over here, this is a denotation, and then when I write here, I am just writing, I am just bracketing this part of the derivative. I did not include this. Is that the right thing to do or a wrong thing, or I should have included that anyways? Well, the point here is that the compressibility, when I am defining, right, the process under which the volume is changing based on this pressure. Now, this process is happening under an isothermal condition, right. So, when I increase the pressure, there is a change in volume. Now, that is the process during which the temperature is constant, right, and that this process I am comparing with what the volume was before that process started, right. So, this is basically the state volume, right. This is a state parameter, or it is a representation of the state, right. And then we started a process in which, say, there is an increase in the pressure and a corresponding decrease in volume. Now, that is the process which is happening under isothermal conditions. So, therefore, I am going to write it in this fashion. Okay, so one condition is where I keep the temperature constant. Now, what if I do not keep the temperature constant? There is no heat transfer happening. There are no other dissipative forms, but there is no heat transfer happening. Then what happens? Do we have a condition for that, or what do we do? Now, we will define something else. Okay. Now, we will define an isentropic compressibility. Okay. We will define an isentropic compressibility, and I will write that as okay. Now, what is this S that I am writing here? Okay. Now, this is entropy. This is the property called entropy, and for an isentropic compressibility, so if I may write it this way, so this is isentropic compressibility, right. So, here for this the entropy is constant, right. In the isothermal case, the temperature was constant. For an isentropic case, the entropy is constant. Okay. Now, what is this S now, entropy? I guess you are familiar with this, but what I will do in the next lecture is do a basic review of thermodynamics, because this entropy is a thermodynamic variable, right. So, let me not gel on that too much, but we will go ahead and do a brief review of thermodynamics, and so we will come back to what we mean by isentropic and entropy and so on and so forth. Okay. All right. So, now let me give you some numbers. Numbers always help, right, to get a feel for how compressible or less compressible and so on and so forth. For example, this is the isothermal compressibility for water right. This is for water. And this is for air, and both these are at 1 atmospheres. So, what do you notice from here? What do you see? These are the numbers that we have. So, that is for water and this is for air. So, what do you notice? What exactly can you infer from here? What you can see is that the compressibility of air is much more than that of water, which is essentially what it is, that for gases the compressibility is much more than water, right. So, we kind of beginning to see a few things about the name of this course on the first slide as to why we are doing this course, or why do we call it advanced gas dynamics as it were. Okay. So, so essentially that is a thumb rule, gases have more compressibility. Okay. Now, so let us find out. So, we have defined pressure, volume, density, temperature, etc., etc. So, what is the relationship between them? If we do have changes in them, how they are related, or if at all, right. So, let us do something simple and develop a few expressions, right. So, say we have a mass of gas, a unit mass of gas. So, we define a specific volume, right. So, therefore, we have density, right, or we can write this as, okay. Then let us do a little bit of math and do this, right. So, basically what I am, this is simple. Here all we are trying to do is trying to get a relationship in terms of the compressibility, right. So, this is the equation 1 that we wrote about. So, this was, we need a derivative something like this, right. So, when I have this expression over here, so dV by dP. So, if you can do this math, right. So, this is simple over here. So, I will do this. Right. So, this is the derivative, right. So, therefore, now I will try and write the compressibility. So, now if I write the compressibility, how does that look? Now, the compressibility is nothing but 1 by V dV by dP, and we got 1 by V as rho into dV by dP, which is over here. So, we input that in there, which is minus 1 by rho square d rho dP, right. So, what we get over here so this is what we get, right. So, what I will do is write this out this way. So, essentially d rho is equal to rho tau dP, right. We will write that, and or we can also write this as okay. So, let us say this is okay. So, what we'll say over here is that in here what you can see, now we have just now said that for a given for a gas, the compressibility is much higher than that of a liquid, right. So, therefore, for a given pressure, the density changes in a gas is much higher than a liquid, you know, because this compressibility is much higher for a gas, right. So, therefore, to bring about for a given pressure, you can see here this is the fractional change in density, right. So, for a given pressure, for air for example, for a given pressure change, there is going to be a much larger density change than compared to say water, essentially because this compressibility factor here is much larger for air than for liquid. Having said that, now let us go back to your previous problem. So, therefore, we have this problem over here, right. Oh, this here, and we said that the pressure change is 1.5%, right. Now, you can do the rest of the math yourself and relate the densities, etc. if you want. In this case, it was incompressible. So, we said there is no change in the density, right. When we consider no change in density, what we found is that the pressure change is 1.5%. But what I can say here is that since the corresponding relationship is for a if I were to consider this as compressible, then the density change is essentially given by this relationship, right. Now, in here, since this pressure change is very small, it is just 1.5%. So, I can say that we have infinitesimal or very small changes in density, and hence I can, it is okay for me to ignore that, and that is, so I can say more or less safely say that it is okay to say that this is an incompressible fluid. So, therefore, changes in density here are not very dominant. So, therefore, it is okay to use the incompressible theory over here. Okay. So, hence I was fine doing this. And then of course, the new the immediate question which we should be asking, that okay, so if we had a flow which was going from 100 miles per hour and it reached up to 150 miles per hour, right, and that caused changes in density which we were able to ignore. But then how far would we be able to do that, or for how larger speeds or how smaller speeds can we do that? If I had a velocity which was going from say 1000 miles per hour and going up to say 1500 miles per hour, would I still see changes in pressure which was very small and causing changes in density which I could ignore? Would that be a possibility? So therefore, I need to relate this now to the speed here, and that is why, that is where when I first said that for flow over airplanes for Mach numbers less than 3 it is incompressible. So now over a period of time with experiments etc., been able to see that more or less it's like a thumb rule that okay, so I may just write over here that for Mach numbers less than 0.3, right, for Mach numbers less than 0.3, the changes in changes in density can be ignored. So therefore, as a more or less thumb rules, for this we can consider the flow to be incompressible. Right. So to answer the question that whether we know a lot about this topic from history and literature etc., well we know enough to know that these thumb rules, right. So people have worked on this over a period of time, so we kind of know these sort of things. Okay. Now the next thing, like I said, the next thing to do would be to do a brief review of thermodynamics. Okay. Now what is this connection of thermodynamics with this? Okay, I said something about entropy when we defined isentropic compressibility, but what exactly, why do we need to study the thermodynamics when we are dealing with compressible flows? Okay. Now we saw that there is, when we have say higher speed flows, okay, or essentially to generalize, when we have changes in pressure which is causing changes in density, right, and these are changes in density which are not small enough to be ignored. Now there should be also changes in temperature, right. Now when we consider those changes in temperature, that's when we need to study a little bit of thermodynamics before we proceed. Okay. So I'll do a brief review of that. Now let's just say, let's just begin with something like this. Okay. Let's just begin with now this P here is pressure, P here is pressure, V here is specific volume. Which is volume per unit mass. Okay. So I'll just write the unit here. Okay. And R is the specific gas constant and T is the temperature. Okay. Now this is something that we are familiar with. Okay. So let me write here, what exactly is this? I hope you can recognize this, right. This is the equation of state. So this is an equation of a state for a perfect gas. There are two things over here. One is equation of state and the other is perfect gas. What do these things mean? Equation of state, perfect gas, What do we mean by a gas which is perfect? Right. Now, all we have done here is taken the pressure, the volume, temperature, etc., connected them by some sort of a constant, etc., and we are saying that this is the equation of state. It is some sort of equation, right? And we are saying this is for a perfect gas. Okay. Now, what do we understand by this perfect gas? Okay. Now, let's just define that at first. Okay. Now, a fluid essentially consists of molecules. I think we are all aware of that, and these molecules are very widely spread about for gases and more closely packed for a liquid, right? And these fluids, these particles or molecules are in constant random motion. They are in random motion, right? So, now if I take, say, a volume like that, say if I take a volume like that, right. So, there is a constant inflow and outflow of molecules across this boundary. So, the number of molecules out here is constantly changing, and we have, you know, free flow of molecules on either side which are in constant motion. Now, when we have these particles, right, it's by nature there is intermolecular forces, we know that, right. Now, if you have two particles which are like really far off, we have particles which are very far off, then they exhibit very small or very weak attractive force, and if they are very close, say like that, then they have a strong repelling force. So, these are the intermolecular forces, right. So, therefore, these intermolecular forces kind of define or kind of control, for that matter, the movement of these particles, right. I think it is kind of obvious to see from here. Now, the thing is, what is this perfect gas? The perfect gas is one when we ignore these. When I say these, I mean these intermolecular forces. For a perfect gas, we ignore these forces, and when we do that, there is a certain relationship between the pressure, volume, and temperature, density, etc., of that gas, and that relationship is what we define as the equation of state. So, which means that if I have a set of you know, some mass of gas, then that will obey this sort of a relationship, provided we ignore the intermolecular forces, right. Now, the next question is, when I define this pressure, volume, temperature, etc., right, do I define it for a, are we considering, say, the pressure of every single particle? Are we considering the temperatures of every single particle when I take a mass of gas, or what am I doing, right? Now, it is important to say that all these parameters here are all defined on a continuum. These are all defined on a continuum, right. Now, what do we mean by that now? Now, what we mean by this is that, let me take these, a boundary like this, right, and I said that the number of particles is changing, etc., you know, and this is just a imaginary boundary. So, what I am going to do here is take a collection of particles, take a collection of these particles, more or less I take such a boundary that these number of particles is not changing, okay. The number of particles more or less remains the same, okay. So, then what happens is that the, okay, let me redraw this. So, I have a boundary like this, right. I have a boundary like this which is big enough, right, which is big enough so that I do not consider individual movements of properties of the particles, right. Instead, however, we are concerned about the behavior of this whole collection of particles, this collection of particles as a whole, right. So, individual behavior of each particle can be ignored. At the same time, now this is not so large enough that it is such a big space that there is agglomeration of particles here, 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 and the particles are not uniformly distributed. Then as a collection of this, we may not be able to say that there is one particular temperature, pressure, volume, because for example, if I have something like this, the temperature here will probably be much larger than the temperature over here, right. So then it is not in, so it should not be so large as well. Instead, if I have a volume like this, this would be a good continuum, right. So that this I can just consider as a group of particles. So more or less around here the number of particles remains same, and I can consider at this particular area for this group of particles a single value of the pressure, temperature, density, volume, etc. So that's what we define as a continuum. So all these parameters, pressure, volume, temperature, etc., are all defined on a continuum. Okay. Now we can write this expression now in some more ways. For example, okay. So here we wrote this in terms of specific volume, right. So we said per, which means the volume per unit mass, right. All I am done here is, because this here is the volume, this is volume, okay. This is volume and this is gas constant. Let me differentiate between this and this. So let me call this as, say, star. This one is the specific gas constant and this is the gas constant. So basically what we are doing is multiplying it by the mass out here, the whole equation, okay. Now what is this n here? So the n is the number of moles in the gas, which essentially this is doing nothing but giving us an idea of the number of molecules in the gas, in the group of gas that we are considering. And I think you will remember that 1 mole of gas consists of (6 × 10⁻26) molecules, the Avogadro number of molecules. Right. So what we are essentially saying here is that for a given number of molecules of that particular gas, this is the relationship that it holds. Okay. This is also for a perfect gas, just trying to look at it a little differently. Okay. Now again, what is 1 mole? What exactly is 1 mole? What is the concept of a mole? It is nothing but the molecular mass of a gas. For example, chlorine is 17, I think, right. So that is the molecular mass of a gas. Okay. So that is essentially the the equation of state for a perfect gas, and I will just give you an example of not example, just give you some numbers, right, just to remember some of these numbers, to be familiar with it, and we will do just a small example and we will wind it up for today. Okay. So for example, this is the universal gas constant. So this is equal to, so this is our star basically. How did I write it? Yeah, star. So this is, for example, 8314 joules per kg mole Kelvin, right, and say specific gas constant is per mass, this is the molecular weight, and for air for example, so for air, so this is equal to 287 joules per kg Kelvin. Okay. So, these are some numbers which you should be just familiar with. What we will do is now is just quickly do this and wind up for today. Okay. Now, all I am saying is that, so air is given, okay, so I have air and the pressure is at 1 atmosphere, right, and that I can write as calculate the isothermal compressibility, right. What is the isothermal compressibility? So, compressibility is nothing but fractional change in volume per unit change in pressure. So, this I can write as right. So, isothermal compressibility. So, how do I find this out? Okay. Now, let us go back to the first equation of state. So, P v is equal to R T. So, if I do this, then I will write the volume as R T by P, right. Now, if I do that, okay. So, if I do that, then all I need to do is dV by dP, right. So, I do dV by dP, and what I do here is that right, this is what we get. So, then if I input that into this expression, the dV by dP into this expression, what I get is this. Hopefully, you should be able to, so 1 by P and the P is given, right. So, the P is given. Okay. Now, what you can see here is that I said isothermal compressibility, right. So, what I mean by saying that over here is that you remember this expression, right. So, essentially what we mean out here is that this change in volume and pressure is happening over a process which is isothermal. So, the temperature is constant. So, therefore, when I did this, right, when I did this over here, I kept the temperature constant, and that's how I calculated the derivative over here. Okay. Now, temperature is constant, meaning that we are not considering any internal forces, obviously, because then there will be changes in its internal energy, and I cannot say that the temperature is constant. So, therefore, I can only calculate the isothermal compressibility from here, right. For example, I have the isentropic compressibility as well. It is the same formula, and we have the same etc. is available. So, I can actually use that. But the idea is that when you use such a formula, you need to understand that what exactly are you using it for. So, if I said find out the isentropic compressibility, etc., you cannot use a process in which temperature is constant. Okay. So, we will have to, still need to think about that. So, I think we will stop over here. What we shall continue to do next is that when I talked about that, so far whatever we did, temperature is constant. So, why are we going to do a review of thermodynamics? Because when temperature is not constant, then I need more variables. Just the pressure, volume, temperature is not going to be sufficient to to study my gas or any process. What I will need further is an expression as to how these variables relate with temperature, and to do that we will need more variables than that, and that is what thermodynamics will provide, right. The concept of entropy, internal energy, and so on and so forth. We will continue to do that in the next lecture. Okay. Thanks.